Okay, next week, I just put together 3 different PDF files. The first one deals with simple regression, which you guys should be good to go already. The next one deals with multiple regression, which I'll start today. The last one deals with what's known as the sign test, which is a non-parametric method. And also do your class evaluation ones for this class and all of your classes. And you guys have the final on Friday of finals week, bright and early, 7:30. And that was not my choice, but that's what they give you. Today is kind of a exciting day because this is our last quiz today. OMG, okay? Now, I guarantee all Fridays going forward, you're going to be missing something in your life. This is our last quiz. We won't do a quiz next week, so. Okay, you guys have any questions before we get rolling? Okay, so let's get into multiple regression a little bit. And you can really go crazy with this material, but I just want to give you a general overview of kind of what's shaking with it. This is multiple regression. And just a little note. Suppose we have minus 1 explanatory variables. Let's just call them x1 through xp minus 1. And what we're going to do, we're going to use the least squares regression equation. Which we're going to denote by y hat is equal to beta 0 hat plus beta 1 hat times x1 plus all the way down the line plus beta hat sub p minus 1 times x p minus 1. So kind of where we're going is instead of having a single explanatory variable, we're going to have multiple explanatory variables. Okay, so in the question that we did before, where we're looking at hours studied and exam scored, hours studied was my explanatory variable, and I was using that to explain your exam score. But you might have more information besides just hours studied. You might have information such as, you know, did you go out the night before to a big party before the exam? You know, and so you could have more variables besides hours studied that you're going to use to describe your exam score, okay? And when you have more than one explanatory variable, you're no longer in the realm of so-called simple regression, you're in the realm of multiple regression, okay? And so we're going to use that for inference. For the population regression equation. And the population regression equation, we're going to denote by mu sub y given x1, x2, all the way up to xp minus 1 is equal to beta 0 plus beta 1 x1 plus beta p minus 1 xp minus 1. Okay. This looks kind of ugly when you state it kind of formally here, but so now, when you step back and kind of think about what we're doing, This is going to make your head explode a little bit. When I have a single explanatory variable x and a single response variable y, what we did before was we made a scatter plot of the points and we fit a nice line through the center of the data. Okay. What if I have two explanatory variables? Well, if I have two explanatory variables, now you have x1, you have x2, y is going vertical, and you have essentially a cloud of points that you have, and you're not fitting a line through the cloud of points, you are fitting a plane through the cloud of points. Okay. So if you have two explanatory variables, you're really working in three-dimensional space and you're fitting a plane through the middle of the points. Okay, now here's the thing that's going to make your mind explode. What dimensional space will I be working in if I have three explanatory variables? You're working in four-dimensional space. Okay. And as a human being, are we able to visualize four-dimensional space? The answer is no, we can't. Okay. And so when you think about what we're doing, I mean, you're fitting a hyperplane through a cloud of points in high-dimensional space. And what's kind of cool is, can we mathematically work in 10-dimensional space or 30-dimensional space? Yeah, no problem. Can we visualize it? We can't. Okay, but this is kind of what we're doing. We're now fitting kind of a plane through a cloud of points in the example we're about to do in four-dimensional space, actually. Okay. All right. So let's do a little example. This is the low birth weight example. And I'll show you what the data set looks like. Here's the setup. My response variable y is systolic blood pressure. And so I wouldn't look like a big bumpkin. That's the bigger number when you do your, I looked this up before class. It's the bigger number when you do your blood pressure. And so what we have is we have a bunch of just newly born babies, okay? And for the newly born baby, they measure the blood pressure, the systolic blood pressure, okay? And I'm going to explain the systolic blood pressure of these infants by two things now. X1 is gestational age. Which is how long the baby was in the womb, I guess you could describe. Okay. And the second variable I'm going to describe systolic blood pressure with, X2, is Apgar 5 score. And this is kind of it's a measure of the health of the baby 5 minutes after birth. So the goal is I'm going to try and describe the systolic blood pressure of these newly born infants by two things: by the gestational age of the infant and by the so-called Apgar 5 score. The Apgar 5 score, have you guys heard of this before? A few of you guys, yeah. From what I understand, my childless understanding, it's a score between 0 and 10. 0 means that the child is really struggling to stay alive after birth. The health is very poor. An Apgar 5 score of 10 would mean the kid comes out of the womb and he's ready to play like hockey or something. He's like really healthy, and so it's a measure of the health of the baby. Okay, so let me show you kind of online here what we have. And I have this kind of blinking, the low birth weight output.txt on our page you can access. And this is kind of what at the bottom here, here's the data set. I believe there's 100 infants in the data set, and quite a few variables were recorded. Here's the first kid right here. The first kid had systolic blood pressure of 43, hold off on gender and toxicity in the hemorrhage thing. But the last two columns, the gestational age of that first kid was 29 weeks, and the APGAR 5 score was 7. So the kid's doing pretty good. Okay? The second kid, the systolic blood pressure was 51, gestational age was 31 weeks, and the APGAR 5 score was 8. What is normal, like, it's like 40 weeks or something? 40 weeks, okay. So I guess all of these kids were kind of a little bit premature, okay? And the third child had systolic blood pressure of 42, gestational age was 33, and the third child, unfortunately, was struggling health-wise 5 minutes after birth. Okay? And you can kind of go down the whole thing here and kind of see the data file. Okay. Okay. So let's do the following. So what we're going to do is, for the setup that we have, we just have 2 explanatory variables. And so our population regression equation is going to look as follows. It's going to be mu sub y given x1 and x2 is beta 0 plus beta 1 x1 plus beta 2 x2. That's going to be my population regression equation. And this is actually describing a plane in 3-dimensional space, if you want to think of it like that. Okay. And we're going to use that population regression equation, and so we're going to estimate that guy with our data. So our data, where my sample size was 100 kids, yielded the least squares regression equation. Now, my least squares regression equation is going to be y hat is equal to beta 0 hat plus beta 1 hat times x1 plus beta 2 hat times x2. Okay. Now, in the case of simple regression, we just had beta 0 hat and beta 1 hat. And we were able to find those guys just using a couple pretty simple formulas. Once you get up into multiple regression, easily finding these quantities becomes impossible. It's not impossible, but you have to know matrix algebra and get into all this stuff. Okay, let's not do that. But what I want to show you is, if I give you the output from R, can you tell me what those parameters are? Okay, so let's look back at R. And if you look back at the output from my analysis here, again, the one thing I want you guys to be able to read is that table right there. Hold on, I'm on the wrong one, sorry. This table right here. Okay. So if you look at this table, so here you have the intercept, gestational age is x1, APGAR 5 is x2. Okay. What do I have in the estimate column? What is that guy going to be in our least squares regression equation? That is going to be beta 0 hat. Okay, that's beta 0 hat. What's that guy going to be? That guy's going to be beta 1 hat, and that guy's going to be beta 2 hat. What do I have in the estimated standard error column? That's the estimated standard error of beta 0 hat. That's the estimated standard error of beta 1 hat, estimated standard error of beta 2 hat. As long as you can read that, you'll be golden. Okay. So let's kind of plug in. So beta 0 hat is 9.803. So this is 9.803 plus beta 1 hat x1. Now beta 1 hat, sorry to keep flicking back and forth here. Beta 1 hat is right here, 1.185. Be 1.185 times x1 plus beta 2 hat is, I guess, 0.488. Okay. So this guy is 0.488 times x2. That's your least squares regression equation. Okay. So I don't know what the population intercept beta 0 is, but what's my best guess at beta 0? Beta 0 hat. I don't know what I don't know what beta 1 is, that parameter in my population regression equation, but my best guess at beta 1 is beta 1 hat, and so on. Okay? So my least squares regression equation is my best guess at the unknown population regression equation. The population regression equation would be the equation that I ended up with if I had data on all premature babies that were born in the world. There'd be millions of premature babies. Okay? If I collected data on all of the premature babies in the whole world and I made a scatter plot in 3-dimensional space and I fit the plane through it, that would be my population regression equation. I don't have that. All I have is, for the 100 kids that I sample, the least squares regression equation is that guy. And I think the least squares regression equation is a good guess at the unknown population regression equation that I would get if I had data for all kids. Okay. All right. So is it okay as far as picking it off the table, how to get that guy? Okay, beautiful. Okay. And so what are we going to do with this guy? Let me ask you this. Let's interpret. Beta 1 hat. So remember X1 is a gestational age. X2 is the APGAR5 score. Okay? Interpret that quantity there. What is that kind of saying? X1 is gestational age. Beta 1 hat is positive. What's that kind of telling you? As the gestational age gets higher, what tends to happen to the systolic blood pressure? The systolic pressure tends to go up. Does that kind of make sense? And for each unit increase in gestational age, for each extra week of gestational age, how much on average is the systolic blood pressure going up? It's going up by 1.185. Okay. So what beta 1 hat is formally, it's the mean. So beta 1 hat, which is 1.185, is the mean increase in systolic blood pressure for each extra week of gestational age. Holding APGAR5 fixed. That's really what it means. So if I hold the APGAR5 score fixed and I increase the gestational age by 1 week, how much extra in systolic blood pressure are we getting on average? 1.185. Okay, that's really what that guy means. Okay. How about beta 2 hat? What does that tell us? So let's interpret it. Beta 2 hat. Well, beta 2 hat, which is 0.488, that's the guy associated with the APGAR5 score. Okay. What's that kind of telling us? What that's telling us is, as you increase APGAR5 score, is the mean systolic blood pressure going up or going down? That's also going up. Okay. And for each unit increase in the APGAR5 score, how much is the systolic blood pressure going up by? By 0.488, holding everything else fixed. Okay. So this is, so beta 2 hat is the mean increase in systolic blood pressure for each extra unit increase in the APGAR 5 score. Holding, gestational age fixed. That's what those guys really mean. Okay? All right. Let me ask you this, one other thing. See, let's approximate. Use of y given x1 is 31 and x2 is 7. What am I asking here? What am I asking? I want you to estimate the mean systolic blood pressure for infants that are how many weeks old? 31 weeks old with an APGAR 5 score equal to 7. Okay? So what is the estimate the population mean systolic blood pressure for 31-week-old infants with an APGAR 5 score of 7. Okay? And how do you approximate that population mean? What do? I'm going to take my least squares regression equation and simply plug in the relevant values. Okay? So what you'll do is, you take your least squares regression equation, which is 9.803 plus 1.185 times x1, which in this case is 31, plus 0.488 times x2, which in this case is 7. That's all you do. And if you punch that in, what that gives you is 49.95. That's my best guess at the mean systolic blood pressure for 31-week-old infants with an APGAR 5 score of 7. Okay, that's all there is to it. Make sense, you guys? Okay. All right. Do you think the population mean is 49.95? Probably not. You think it's probably around 49.95? Probably. What do you think we're going to do next? No confidence interval, right? But we have to wait till Monday. Okay. Yeah, we'll do that on Monday.